Yes. Welcome everyone, and thanks a lot. Thanks those who have resisted till the end of the program, more or less, and it was a lot of fun and a lot of effort, I have to add. So now I have a Christmas vacation, which is for an Italian the hardest time of the year. So family business and so on. So now this has been my vacation time. Then I go to the real job. So
You realize that this is on tape, right?
not yet, not yet. It's recorded, okay, but it's still. I mean, I'm still within the range of irony, more or less. Anyway, so okay, so yes. Now, okay, so today I would like to present some work that I've done with Davide Faranda, Paul Manville, and Jeroen Wouters, where we have been using some ideas of extreme value theory. It's work done in the last years with various collaborators, and now we are writing a book on this. And this is a sort of an application of more than anything the concepts, more than the more formal result, and with the perspective of trying to get more rigorous things in the future. And so the idea is to use extremes as a way to characterize and study critical transitions. So this is the idea. And the image you see here is let's say a plane Couette flow, which is featuring alternating patterns of turbulence and of laminar flow. And we will look at this problem. Now, so this is the plan. So we briefly introduce, we use the word critical transition or tipping points or whatever you want. And then just say a few words about extremes. And yesterday, George has explained this in much greater detail, but just to basically introduce the notations and mention what we can how we can push forward the extreme value theory in dynamical system in some cases, and then mostly, in fact, discuss how we can use these ideas to study a prototypical system featuring stability and critical transition, like the plane Couette flow. Okay, so first let's look what is the cartoon of a critical transition. So the cartoon of a critical transition is of this sort. So we have, this is a famous picture of Lenton et al., a paper of 2008. And somehow we have, we have to interpret this, I think, as a metaphor of a system, like rather than taking it too literally. So what we have, in this case, we have one-dimensional a system in an energy landscape, a one-dimensional world. So we have, say, maybe an overdamped oscillator in this potential and driven like by a Langevin equation. And when we have sort of a steep, we start with our reference, with our little ball in the right-hand side on the right potential well, and we have noise, and this ball is driven like that. And of course, only very rarely will jump to the other minimum of the potential. And somehow, when this well is deep, we expect to have a sort of a fast movement because the force that's taking the system back to the minimum is quite strong. Then, if we alter a parameter, and this potential well becomes shallower, we have larger deviations for a given forcing, slower recovery, and then at a certain point when we have the bifurcation, the system will jump to the other case. And of course, I mean, there are infinite examples where this is relevant. Of course, the whole idea of stochastic resonance comes from this, adding some periodic forcing and so on. So this is just the picture, but of course, we can and if we have this system, we can actually compute precisely a lot of these properties. Of course, when we start to go to higher dimensional system, things start to become a little more complicated. So this is a work that now I'm doing also with these pictures are taken from colleagues on the internet shamelessly, and but this is again just as a qualitative. Imagine how I'm working on this problem with Tobias Kuna, and so as an example, if you have a 2D energy landscape, immediately things can become more complex in the sense that we can find path of transition of minima action between local minima, and still the system might look like being one-dimensional if we have just a simple valley and simple system of valley and passes and peaks. But of course, the linear trajectory is not at all related necessarily to a projection. So when we go to 2D to 1D, from 2D to 1D, things becomes non-trivial. In other terms, the dynamics of the minimum has nothing to do with the minimum of the dynamics. And the real world we know is the trajectory will look more like this, okay? So this is just, again, a qualitative picture. So in this case, the problem of what is the effective when the potential already starts to become not so trivial, and what happens when we change a parameter controlling this energy landscape, well, maybe it's not so easy then to translate this picture, in fact, to this picture, okay? So we have to keep in mind that if we get the qualitative properties might look like the quantitative properties might be not so right. We have to keep in mind that in these sort of problems, if we make the errors we do by making a mistake, a bias in the estimation of the potential are exponentially large in terms of time scale. So that it is a delicate problem. Now, of course, when we go to more complex systems, we immediately realize things can, again, qualitatively look like the first cartoon, but things can be more difficult. So recently, people have been classifying three classes of tipping points, Archwin et al. From Exeter. So parametrically induced, which would be the sort of traditional bifurcation, or you can reach it with a quasi-static change of a parameter. Rate-induced, where instead the change of a parameter has a finite rate, and the noise-induced, which is actually, in fact, related to a tunnel effect, like in the case of the double potential wave, and this depends on the amplitude of the noise.
Sorry, what is rate-induced?
It's when you have a change of we have a dynamical system with a parameter which changes, say, linearly with time, with a finite rate, not a zero rate. Of course, these and these will be substantially different when the rate of change of the parameter starts to be comparable to the internal timescales of the system. So that's the basic idea. So, and okay, so the Archwin, it's a colleague from Exeter.
We sell car.
No. Okay, so sorry, I misspelled. Okay, sorry. Then okay, so we have.
I just want to see it, so I need a journal title.
It's in archive now, and it's been also published, I think, in Physical D, maybe, but I'm not sure. I read it in the archive. Yes, it's very. Okay, so in the case of the Earth system, there are various interesting problems of this sort, and I mean the most classic and most outstanding is the problem of the transition between. I mean the Earth seems to be now in a bistable regime, so we have co-presence of our present climate and potentially a snowball. So ice covered the planet with much lower temperature, and by changing the solar constant, we can change from one to the other, and at the present value of the solar constant, the system is in fact bistable. And if you start to study this transition, you see that it's really not easy somehow. Or if you want, there are many ways to characterize this transition, so the properties of the two systems, and the properties of the transition between the two systems, and clearly just a simple picture of a potential well doesn't do justice to the system. So you can as an example, characterize it with the temperature. Remember that if you have a time series and I have a bistable state, I can always construct an equivalent 1D potential, but then I am putting all the, it's not trivial how to construct the noise and how to interpret the potential. Anyway, and as an example, if you want to study this transition, you can try to find some indicators, some precursors. So something that we have found is if we introduce a quantity like efficiency of the system, which describes how efficiently the input of a radiation is transformed into mechanical energy, and it has to do with the temperature differences. You can construct it like a Carnot efficiency. You see that when you get close to the transition, this thing becomes large, basically because the negative feedbacks of the system are weaker. You know, we're just trying to get some indicators of this. Now, you also find other things that if you change another parameter, which in this case is the rate, the length of the ear, you have that the width of the bistable region can decrease and then crash to 0 for a certain value. So you can lose these properties of bistability. In other terms, if I construct a simple, basically just from time series analysis, if I construct a model, I don't have much predictive power. That is I construct always ad hoc model. So we would like to try to find something that is somehow stronger than the simple model we have seen. So as I said, how do people use time series analysis to study tipping point? So basically there are some prescriptions, and this has been described paper by Sheffer. And so basically people, as I mentioned in the first cartoon, look at the so-called critical slowdown, so somehow near a tipping point. Remember, let's keep in mind the image of the potential well. The fluctuation becomes larger and becomes slower, and the correlation, autocorrelation increases, and the variance increases for a given forcing. So this is true, of course, assuming that the noise it does not depend on the, or weakly depends on the state. And, but in fact, there was a point made by a colleague, Ditlevsen, that if I wanted this picture to stay, I need that when I have a tipping point, all these three elements come together. Instead, sometimes only part of them are present, meaning implying immediately that the first cartoon I showed is not so complete. Now, these indications, these qualitative properties have, are easy to detect, which is good, but they have some limitations in the sense that, as an example, we don't have an obvious threshold beyond which we can call, okay, we are getting to a tipping point. First thing, that's the first problem. The second problem is that, of course, it is not, if my states are not fixed point, but they have interesting dynamics, the internal fluctuations are not obviously related to a fixed point that does not really exist. And of course, we can, in general, people try to look at departure from Gaussianity, but if the time series from the beginning is not Gaussian, of course it will depart from Gaussianity because it's never been Gaussian. There is a problem again here. So of course we can think of, a long-term goal is to use Friedrich-Wenzel theory to study in a practical and effective way tipping points. We are not definitely there, but let's see what we can do a bit somehow in this direction, but definitely with a weaker approach. So somehow, in general, the problem is that we lack, using these indicators, very important properties we want if we want to study qualitative changes. Because here, when we study tipping points, we're looking at qualitative changes. So we would like some degree of universality that allow us to make a statement, okay? Because if we cannot, it's not that we can usually distinguish a variance of 3 from a variance of 5. We would like to be able to set a threshold that gives us general information. So extreme value theory provides some indications, some universal properties, and we would like to use this property in this direction. So we will use the anticipation is that we will use extreme value theory to look at large fluctuations of my system. So I have to use an observable. I have to use a large excursion of this observable, and I will I will try to identify a tipping point when, if I change a parameter of my system, this excursion change from being of one nature to another nature. So in particular, we want to detect when our distribution moves from being viable, so limited, to fresh. So somehow the Gumbel distribution, which has shape parameter 0, it's the transition between these two qualitatively different properties, will be our, let's say, our threshold. So c equals 0 will be our threshold, saying I can have very large fluctuations. This will become clearer, but just to give you an anticipation. So somehow the idea is studying sensitivities of extremes near tipping points and using the strong sensitivity to exactly to assess this. Okay. Now let's go back to our physical system, the plane Couette flow. So plane Couette flow is it's a very, I mean, it's something like one of them. It's a very classic problem of fluid dynamics. So I have a region between two plates which are moving in opposite direction at velocity uw, and I can introduce my fluid as a certain viscosity nu, and I can the distance between the two plates is 2h, and I can introduce the Reynolds number. And the Reynolds number characterizes my system basically. So that's again, this problem has been studied since a long time. So what is this system is a sort of a riddle, because the linear profile is actually linearly stable at all values of the Reynolds number, which is a pretty bizarre thing, because in fact we know very well that the laminar profile is observed only on a finite range of the Reynolds number. So if I have a very strong shear, that flow will be definitely turbulent, as one in fact expects. But it's very important, the linear velocity profile is linearly stable, and there is a very small but finite basin of attraction around the linear profile. So remember that, qualitatively what happens? If the Reynolds number is low, I have one basin, I have one attractor, which is my fixed point, my laminar flow. When the Reynolds number is very large, so let's say extremely large, I have I have multi-stability, two disjoint attractors. One is the fixed point, one would be my turbulent flow. And there is something in between, there is a boundary, okay? And actually we can study also the boundary, but with other methods. Now, so if we set ourselves in the region where we observe turbulence, we said that there is always another, this is not the unique attractor of the system. And a lot of research is devoted to finding, in fact, how big, and it is very small, is the laminar attractor. Okay. Now, so we are in a situation of multi-stability. We are in a situation where we have an easy one control parameter, the Reynolds number, and it seems that it's the right kind of problem. So this is the phenomenology of the plane Couette flow. So for Reynolds number, say below 280, we have laminar flow. For Reynolds number above 415, we have a featureless turbulence. For Reynolds number at intermediate value, a lot of interesting things happen. In particular, above 325, you observe experimentally and numerically sustained spots or stripes of turbulence, the one I showed at the beginning. And Lore Tuckerman, Buckley, and Manville and many others have been studying this for a long time. And then there is another range between 280 and 325, where turbulence is only is not really persistent, is transient, but it can last for a long time. But from our point of view, we have three regimes. So laminar flow below 325, stripes of turbulence up to 415, and featureless turbulence. That's the three regions we have. And okay, so this is the kind of properties. And what we will do is start from the featureless turbulence and come down, basically. Please.
When you say it's an open problem, it's numerically it can be simulated.
Yeah.
There's no theory.
Yeah. There is the problem is that especially numerically it's been simulated. We will show some simulation as well. Actually, not very fancy ones, but yeah. But the problem of how these structures are created and how these are related to spatio-temporal chaos, this is still it's a very difficult problem as far as I know. So this is the kind of so there is these structures are robust in the sense that you find them experimentally, you find them numerically, so they are extremely real. So this is a phase diagram of the problem where I see that basically these patterns emerge when I have a large enough aspect ratio. So when the system is really extended, there is an interaction between local and global properties, and this is the Reynolds number, which is increasing. And there is a concept of the minimal fluid unit, which basically describes the unit, the volume over which you can have sustained turbulence. And this is there is somehow a finite volume where we have, let's say, which constitutes the unit of the system. So this is the kind of let's say of image we get. So if we start with the let's say with the Reynolds number of 420 and we reduce it slowly, you see that progressively we go from featureless turbulence to a banded structure, 3 bands, 2 bands, 1 band, and then the turbulence is lost. So this is what is observed. It's actually quite amazing. And interestingly to see that the intensity of the turbulence does not decrease much, but it's a special extent that changes. It's very...
Each horizontal line is a snapshot at a certain time?
Yeah, which is also a snapshot at a certain value of the Reynolds.
The bands don't move?
Huh?
The bands don't move?
No, the bands don't move. No, the bands are stable. Yes. It's, this is the... Huh?
Bizarre.
It is bizarre, otherwise, yes, it is bizarre, in fact. And so anyway, this is the intensity of the turbulence doesn't decrease, but it's literally some parts are dead. That's what happens. So it's a local process, and the problem is at the boundaries, of course. Nobody has understood what happens really at the boundary. Now, let's very briefly, because we have seen this several times, so now we want to look at extremes, and of course our natural quantity, here we have a natural observable, which is the turbulent energy, because the turbulent energy is 0 when we are in the laminar flow, and it has a finite value when we have the turbulent state, and it is actually also a distance from, so it's actually a well-defined quantity. But so now, of course, we want to look at extremes, and what we have seen in this several times in this program is that one way of looking at extremes is choosing the block maxima from a time series and then considering the statistical property of this block maxima when the length of the block goes to infinity. So we know that for a large class of phenomena and for I mean from an empirical point of view and for a lot of mathematical objects which have been discussed in detail, these maxima converge asymptotically to the cumulative distribution converges asymptotically to the generalized extreme value distribution, which is a free parameters distribution. So where we have this is the important point. So we have a lot of distributions, in general non-parametric class of distribution that end up in just a 3 parameters family. So we have really convergence in functional space, and this thing attracts a lot of functions. So we have 3 parameters: the location, the scale, and the shape parameter. So this mu and sigma can be, in fact, can be absorbed in the construction of the linear scaling that George discussed yesterday. And but what instead gives you the qualitative properties is the k, is the shape parameter. And as we see, we have three possible situations. If k is negative, we have a Weibull distribution, which is upper limited. So this maximum do not shoot to infinity. If k is larger than 0, it's a Frechet distribution. So we have very extremes that can be as large as they want. And then there is the limiting distribution, the Gamble. So of course, going from here to here, from here to here, we change qualitatively the properties of our system. So this is, as I anticipated, what we are going to look at. So, of course, the problem of studying extremes, so it's we can write the asymptotic results, but looking at data is a problem because extremes by definition are rare. And so it's hard to get good statistical properties. So if we want to have high statistical accuracy and look at true extremes, we need a lot of data. So there is always a problem. So also for this reason, it is important if we want to use extremes as indicators of something, trying to look at some robust properties of these extremes so that we are not so terribly constrained by that data scarcity. When you look at extremes, data are by definition always scarce. Now, the results what has been found in the last years is that, in fact, if you take, I will use on purpose rather sloppier language than discussed by George. I mean, if we take systems which are mixing enough, and in some sense we can say for all practical purposes systems which are chaotic, and as an example, axiomatic systems obey these properties, and we choose observable function like functions of the distance between an orbit and the point on the attractor, well, choosing suitable functions, we end up having that the maxima, block maxima of these observables do obey extreme value law. So this is, I think, a building block of the idea that extreme value law is a theory that can be used for describing the properties of deterministic dynamical system. So that basically the fundamental property is that the G has to have a maximum in the point. So we are studying closed recurrences. Now the interesting, very interesting aspect is that the extremes inform us. So depending on the functional form we choose, there are three, let's say, classes of functional form that give us automatically the output. This is the most important thing, is that extremes, the parameters of this extreme value distribution, look at this D, are related to the local geometrical properties of my system. So the extremes, since I'm studying recurrences, extremes allow me to there is not just a diagnostic tool. We learn about the local geometry of the problem. So they give us some very intrinsic properties. So this is, again, why extremes is a good method to study the properties of dynamical system, because they are really a very intimate property. It's not, it's quite, I think it's a quite powerful concept. Now,
you underestimate.
Okay. This is good. Okay, so it is. Okay, so what is an extreme then? So basically, if we take our point, zeta, these blocks maxima somehow are related to close returns to zeta. Okay, so this is the basic idea. So that's why we are sampling near zeta, and that's why we get information about it. This is, this is in phase space of my dynamical system. So this is my point zeta. My max, I'm studying as observable of the function between zeta and an orbit. So these functions achieve a maximum for zeta. So if I'm close to zeta, I get high values. That's how I get the maxima. And okay, now we take a detour. So if instead of taking the point of view of block maxima, we take the point of view of looking at peaks over threshold, so we select the extremes in a different way. That is, we set a threshold and we look at what is above such a threshold. So this leads us to another family of functions, which are in fact closely related, the so-called generalized Pareto distribution. And in fact, one can prove that if the variables, stochastic variables, obey the mixing conditions that we need to derive extreme value laws from the GEV point of view, we get that the peak over thresholds are distributed according to generalized Pareto. So somehow extremes are extremes, no matter how you look at them, if the system is mixing enough. This is important. What George discussed is that if one of these conditions is not obeyed, there is still a relationship, but there is a change in the shape parameter. But still the theory applies. It's actually quite extremely fascinating aspect. So, yeah. Now, in the case, if I take a peak over threshold, the picture somehow becomes even clearer, because an above over threshold event is literally a return to a radius below than a certain threshold. So I have an exact equivalence between studying extremes and studying the mass included inside this ball, the mass of the attractor included inside this ball. And if I construct some scaling laws if this mass has a scaling law, automatically I will get a power law in my extreme. And this is basically how I end up with generalized Pareto. In fact, we don't need we can do something a little more general than assuming a power law in the scaling of the mass. What we have found recently is that it's enough to have a power law modulated by a slowly varying function. So which can accommodate, we believe, a little more the fact that there is fine grain inside. So anyway, the problem is this is the case for this distance observable, and with some substantial work, what one can find is that in fact one can readapt the theory to study the properties of so-called physical observable. So instead of taking a function of the distance from the orbit and a point in the attractor, I use a function of the phase space, which say is maximum at infinity, say. So something that it can be a sum of the squares of the variables, or can be whatever you want. And this is how a typical observable would look like of a dynamical if the dynamical system represents a natural or engineered system, or a natural or a social system, the observable will more likely look like something like that, an extensive quantity, as an example. So in this case, you can still construct a theory. Let's say it's problematic to construct the geometrical set that define your above threshold events. But there's been a couple of contributions on, and both using the block maximum approach and the peak over threshold approach, you end up with the same result. Somehow you find there are some uncertainties on the geometry, but still, anyway, the basic concept is that you find that regardless of the physical observable you choose, the extremes of this physical observable should be distributed according to a sort of to a universal parameter, shape parameter, which is 1 minus 1, the inverse of the sum of the stable of the dimension of the attractor in the stable direction, plus 1/2 of the dimension of the attractor in the unstable direction. And this 1/2 comes from tangency conditions. And anyway, the result is the qualitative property is that since the physical observable have bounded fluctuations, I expect a variable. And also, if my system is very high dimensional, my variable will tend to a gamble. Okay, but let's say, so this is important to keep in mind. I have a robust result saying if I study a fluctuation, this is bounded and the maxima should be variable distributed. Okay, so this is the general result. Now, let's try to go back to the qualitative properties. So the results I said apply in this case. So, you know, I have an attractor which is a horrible object of this sort. This is an orbit. I study let's say the maxima of x squared plus y squared, and I end up studying the local properties of this point. If the system is axiom A, local properties give me information on the global properties, I'm very happy. Now let's assume that my system looks a bit different. My system looks like this, okay? Looks like two the attractor is almost divided in two parts, and there is there are three time scales, say the time scale of mixing here, time scale here, and a very slow time scale where we jump from one to the other. So it's a quasi-bistable system. So what happens, in fact, that if I study my extreme value properties and I start from here, there will be, for a certain time scale, I will only look at the properties of this guy. And instead, if I start here, I will look at the properties of this guy. Then, if I wait a long enough time, I will start to jump between the two, and I will get some sort of global properties. So we see that in practice, we should not believe too much our results, or better, we have to interpret them. Some system might provide interesting properties, and even more if I have disjoint attractors, of course, and maybe noise can let me jump. But now, let's assume I am here. And what I have to keep in mind is, let's assume I am in a situation, or here it's quite similar. I am observing the system over a long time scale, but still a time scale which is short compared to these jumps. I will construct my statistics of extremes. If I wait a long enough time, suddenly my system will explore. As an example, let's say my observable is the distance on this direction. I will observe strong excursions. Okay, so I will observe some sort of monstrous events, which are not described by my statistic of extreme, because these are very low probability paths that I don't find. So I will accumulate a good statistic of extreme, and suddenly I will get strange events. So I think this is a simple conceptual model for. There is a sort of now a mythology, I don't know, of words that are used to describe these events, dragon kings, black swans. I think this is basically what it is. So these are events, there are variants, and I'm not going into details, where I have events that are not extremes, that are in some sense extraordinary, are more than extremes, are so rare that they are not captured, just because I'm exploring part of the phase space, which are rarely looked at. So, okay, so this is, so what happens is, so now we understand what is our image. Let's go back to this graph. So if I change a parameter and my system goes towards a critical transition, what I will find is that at lambda crit, if lambda crit is the critical value, I might observe, if I choose the right observable, of course, I can choose a wrong observable where everything is shadowed, but I will observe a transition between a viable distribution to a Frechet distribution, because this will exactly be the indication that I start to have extremely large jumps, which are not viable in any sense. Okay, so that's how we want to look at. And so this is the Plain-Quet flow, and this is the result. If you change the resolution, the structure I have described you is extremely robustly represented. The number change, the threshold change, but the properties are absolutely, very similar. So we have laminar flow, oblique bands, featureless turbulence for any resolution. We choose any reasonable resolution. So what we will do is start from here, decrease the Reynolds number, and study, as a function of the Reynolds number, the properties, the shape parameter of an observable, which will be the fluctuations of the turbulent energy. That's it. Okay. Now, let's look first at these two graphs. So these are the fluctuations of energy for Reynolds number 300. We are here in this case, so we still have turbulence, no problem. And this is 277, which is closer to the critical value. So we see here that we have fluctuations of energy which look extremely, like nothing too fancy. And this is the this probability distribution of this fluctuation. So my system has typically this energy, there is fluctuation, and the system has positive fluctuation and negative fluctuation. They are not very different, okay? But it's quite Gaussian, but this is not important whether it's Gaussian. It's interesting to see that, you don't see a qualitative difference between left and right, but now let's go at 277, close to the transition. So if you see, the positive fluctuations are not very different from here, but look at the negative. We start to have a long tail. And we see it graphically. So we have some events where, in some cases, my system has this very long excursion to very low value of the turbulent energy, and then it recovers. And then after a while, very rarely, it has another extremely distant excursion. Okay? So somehow this is the system is feeling the presence of the other attractor that, remember, it's always there. The laminar flow is always an attracting set. And these are basically the results we obtain. Let's look at the right-hand side, and the top. So the top is Reynolds number versus shape parameter of the maxima, red, and minima, blue, of energy. So the large fluctuations and the small fluctuations. So as we see, in the case of the maximum fluctuations, the shape parameter is always negative and doesn't depend at all on the Reynolds number. So we have limited, so it's not Gaussian, in fact, because it's the shape parameter is negative, but we have, let's say, healthy, large fluctuation of energy. The size of this fluctuation, of course, will be much larger here than here because we are renormalizing. This is the whole idea of extreme value law. But instead, the negative fluctuation of energy change nature. So as we see, for high values of the Reynolds number, actually they are statistically very similar. And then when we approach the critical value from above, the tail index of the minimum goes up, 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 and crosses zero exactly at the value of the bifurcation. So somehow, I think this is good because this tells us that there is a qualitative change. So literally the system at a certain point does the first infinitely, some sense, large negative excursion, which lends it to the stable fixed point of the laminar flow, and then it's stuck there, and it doesn't recover anymore. So this is the effect, what we find. Okay, now, we can repeat, as I said, we're looking at extremes, so there is uncertainty, and there are, of course, it's not easy to integrate this model and to collect enough data. So there are various theoretical models that are proposed to study these sort of problems. This is a very simple model by Barclay. It's a system of two ordinary differential equations with the multiplicative noise, and the x and y represent, let's say, modes, turbulent modes. So x squared plus y squared is some sort of surrogate of the turbulent energy. And what we have is that for mu nu smaller than 1/4, we have, in fact, a multistability. 0, 0 is the laminar state, and then there is a turbulent state. There is something which has a non-zero expectation value of x squared plus y squared. Now, what we do is, in this case, set ourselves in the multistable regime, and then change a parameter u, which describes again a sort of viscosity due to turbulent flow. It's a control parameter of the system. So what we want to find is the probability is exactly studying the excursion of energy, of turbulent energy, as a function of this u. So this is.
Can I ask a question?
Yeah.
Why in the y equation you get dy dt is minus nu x? Why is this minus nu x term a Fiscus effect? That's what I'm trying to see. I see that. Because it's not acting on y but x. So I didn't, because it, terms like that could also be rotational with a disc.
Yeah, it's.
That's not, I
I take this as just as a toy model. I honestly don't know the physical derivation of
the
this.
first term in the top equation, okay, that's clearly damping
Yeah.
x. The second one, I can't see offhand why mu is the new term with the new
Yeah.
is actually damping in y. Because
I
don't see
I
damping in
honestly
y.
yeah
Okay.
This
No, but
analog thing happen with convection atmosphere, deep convection.
Mm.
Yeah. If you write down convection energy cycle, X will be kinetic energy, and Y will be what we call cloud warm function, extreme potential energy. Then, as convection grows, kinetic energy grows, then it consumes potential energy. That is minus nu x physically. Well, just possible.
Okay. Okay.
Yeah, so that
Okay.
makes
Actually,
sense.
this is good to.
And why? Yeah, I don't know why.
There is, this is the
That
this,
is kind of forcing term.
this nonlinear term conserves the turbulent energy, but let's say yeah. I mean I'm here. This is I'm using this as a toy, but yeah, I don't.
Yeah, important thing is you didn't emphasize the C is multiplied on X.
See, yes, this is a multiplicative noise. Let's see.
Yeah.
Let's see what we find here. If we increase u, which means in this sense, in this model, amounts to increasing some viscosity, some additional viscosity. So again, let's look at the minimal and maximal excursion of my energy, of my turbulent energy. So if we increase u, the maximum excursion of the energy and the minimal excursion of energy for u close to 0 are very similar. And the maximum does not, the large excursion of energy are not very impacted by this u. So somehow, again, we see a differential impact depending on what kind of fluctuations we look at. And what we have is that there is a critical value, 0.3 something of u increases this way, where the tail index of the negative fluctuation of energy crosses 0. And this exactly corresponds to what is the critical point when basically if you initiate the system with a turbulent state, it will jump very quickly to a laminar state and stay there. So somehow again you find this property, and this property, and you find this actually even more in an even simpler case, which is the first one I showed. So we finish with the cartoon I started from. That is, if we start.
Yeah, I want to understand this.
Yes.
U is measure of
Viscosity.
Noise. Viscous noise.
Yes, exactly.
So that makes sense.
Yes. So this is what you obtain for two different values of mu, of the combination of mu and nu. But you have again exactly the same properties. Now, if we go back to my initial system, that is the double well potential, we can repeat this. And what we find is again, so we change, so this is our potential, and let's say we have a parameter C that we are going to tune, and it's exactly the parameter that's going to flatten one of the two potential well. We repeat all the procedure, we study the extreme value laws of these guys, and this is the critical value, 0.22 for our choice of parameter, this doesn't really matter, at which we are going to have a flattening of the potential, and what we have is that whereas the large fluctuations on the right-hand side are not impacted at all by this change, because the potential look more or less the same on the tough side of the potential, we have that k for the tail index for the minimum decreases, and crosses 0 for this value. And this is exactly the value when we have the bifurcation of the system. So this is, I think, so somehow we see that the qualitatively similar properties are obtained on three actually quite different levels of model. Very simple one-dimensional model, already a slightly more complex model where we have multiplicative noise, and actually for a full fluid dynamical model. But the phenomenology, the qualitative properties are the same, and I think this amounts to the fact that we are using an indicator like that of extremes, which obeys which has universal properties, and which is able to detect the qualitative changes in the properties of the tails of the distribution. So this is the main message. So somehow extremes can be used to study critical transitions, and when as in the case of the Planck wave flow, when we reduce the Reynolds number, and I think this can apply for much more general system. And somehow what you really observe is that the change in the properties in the large negative fluctuation of the energy are related to the fact that the system in its turbulent state somehow perceives the presence of a laminar state, which is getting closer and closer. So some sort of metaphorical energy landscape as a lower ridge, but it's not necessarily just like this. And somehow if you look at the smaller models, simpler models, you tend to get the single result. So thank you very much for your attention. Sandro. Sandro, I'm looking at you. Yes. Yes.
Can we make it very general? I guess the not sure is why you took the flow. Why you took?
We took this for a very practical. No, for a practical reason, because the problem of these transitions, it's really studied very extensively. It's not clear, and people are desperately trying to understand, to somehow to detect precursors of the transition, and studying the mechanisms of this transition, and somehow in this case, and these are related. I mean, and people are studying energy fluctuations to look at this. So this seemed like a good test case to test a more general hypothesis. It's not a cooked duck example. I mean, when you look at something like a two-well potential, in some sense, is a cooked up example. You know what you're going to get. You can actually solve the problem analytically. So instead, in there, you can't. I mean, we don't know how to solve it, but still we get the same result. Then, I mean, this doesn't answer the problem of how the transition takes place, but actually it could, because you could try to study the indication is that the transition occurs. This was the original actually concept by Paul Manville, that said, so that I was encouraged to think about this problem, is that you have sometimes these very low energy values and the system wobbles, sometimes it dies. So these extreme events, studying the extreme events of the events corresponding to very low values of energy and how this goes might help you understand which are the mechanisms by which you have loss of turbulent state. That's
yeah, I guess I know much less than you do this problem. But I would look at this problem as a issue of weakly nonlinear instability problem. And that I'm pretty sure there is extensive literature along this line.
No, there is an enormous literature on this problem. This is just a different.
It's not obvious we can make a breakthrough by adding noise to this problem. So that's
there is no noise added to this problem.
Well, I thought extreme is kind of noise in this context of this global stability.
No. In this case, there is no noise. This is a determinate. This is not. This is another story. But if we look at the original system, there is no noise. It's internally generated.
No, you're right. But kind of interpretation would be the reason to look at extremes would be extreme works as like a kind of trigger for.
No. In this sense, it's a trigger. No, it's not a trigger. It's an indication that you are going through a path of. These things are still a little cut off, but I'm getting close here and coming back. That is the sort of, and I go from this situation to this situation. So this is the turbulent state, this is the laminar state. When suddenly one of these things branches and goes in, because from the point of view of these scales, a long excursion is infinite. That's the point.
Yeah.
And that's why I expect to see a viable distribution morphing into a Gumbel distribution, because suddenly this excursion is fine, and then suddenly there is something which is much bigger, which is this little filament, which will be a aborted uptempo of transition, because still I am below the critical value. Of course, if I'm here and I add some noise, I might jump. That's still another aspect. Yeah, that's still another. So yeah, so you could see that if you get, if you are close to the transition and you add a little noise, probably you start to see these events, or you might get.
I guess, well, the real issue is question of motivation and what you're actually doing.
Mm-hmm.
And I thought motivation was to demonstrate importance of noise-induced instability in climate system.
No, this is not the region. No, there is a general. There is a general. No, it's the problem is no. The problem is how to characterize this critical transition. Not in particular about climate. Climate is a good, extremely good motivation, and I think and how to look at time series, how to use time series to study and infer properties. That's.
Can I ask on the observable you choose? I mean, you started from dynamical systems theory, so turbulence is a very high dimensionally, possibly infinite dimensional dynamical system. But then when you apply it, I think it's a good idea to apply it, but then you choose a pretty special observable, which is the turbulent energy. Now, wouldn't it make sense possibly to consider other observables as well?
Yes.
And then see perhaps for this union of observable really good sign of a precursor.
Actually, it's because you should get similar properties. Actually, an idea. It's a good idea. One idea could be, in order to increase the signal to noise ratio, is to, once you have a time series. I mean, once you have the integration of the model, to take various observables, which are not a linear combination of each other, and then study which are independent. Then, as an example, maybe study the sum of the shape parameter that you get in each of these, because what you do is that basically you are removing the mean values and everything, you get just the shape parameter. And in this way, probably, actually it's a very good idea, you could reduce the noise due to the finite sampling.
Yeah, and then one could really do something new in the sense that you really apply extreme value statistics to several observables.
The multivariate extreme value theory is actually an extremely difficult object. But as I'm now looking in terms of practical thing, as basically to get an indication whether you are getting close to the transition. I mean, what you should get in particular, let's go back to this figure here. So you see there is noise, of course. Let's assume I take various variables. They should all behave qualitatively like that. They will. And they will cross zero in the same place, because as soon as I choose an observable which has a different value in the two pieces of the attractor, I get the same qualitative property. So probably I will have different observable which all have, say, this sort of, will have a monotonic change. So near zero, if I sum many of these, I should get a better precision probably. So it's a sort of an index. It would not be the extreme value theory of the sum, but will be an index which I can construct. This is actually a very good idea.
Yeah, I mean, for me, somehow the attraction of the extreme value theory is that you have few parameters, namely three. So it means somehow this thing should be more. I mean, there should be a statistical procedure which should be somehow pretty robust. So the question is somehow how large actually the extremes you need. How large extremes really have to be to see this kind of feature. I mean, what you somehow pick up is somehow in the one-dimensional model the change of curvature.
Yes.
Yeah. But I mean, wouldn't it be interesting somehow to look in the data and just somehow restrict yourself more, somehow trying to demonstrate how robust and powerful is somehow the statistical method. It just works somehow with less extremes, and just compare it, I don't know, with other Fourier or other techniques, and to see if somehow you get a better result.
I mean, studying the sensitivity of this with respect to the choice of the extremes, you mean?
No, somehow, I mean, it's clear. If your time series is long enough and you have enough data, any statistical approach will more or less work. Yeah. So it's just you can do the overkill. I mean, Kolmogov's mean if you fit everything. But if you somehow have the fewer data you have, the harder it gets. And so somehow the extreme value looks nice because you have few parameters. The disadvantage is that you have
but
you need extremes. Yeah. So
yeah, but you know, it's few up to a certain point. It's 3, meaning that you need, I mean, thousands, 1,000 order of a candidate to get a very good estimate. Not often you get, which mean in this case 1,000 of aborted attempts of transition is not so easy. So there is a problem of data limitation. Here we were already at the limit of our abilities, and this is still, it's dirty. So, thank you.
Has there been any work on trying to apply instanton type ideas
Yes, yeah.
to the full high dimensional problem? I know for some of these model low dimensional problems, but to the coed flow problem itself, do you know, are you aware of it?
No, I know. I mean, conceptually, I guess it is. I mean, it's of course the sort of would be the solution in some sense to find the instanton. I mean, this was I think the first picture I showed. This is from Van Heijden. In fact, this image here. Where is it? Yeah, I mean, sorry. Yes. This. Compute this thing. Yes. I don't know, honestly, I don't know. But I think it's a quite very complex problem.
Yeah.
It's not so clear that you don't have degeneracies, because you can have some problems where it's not so obvious, I think. But
Questions? If not, let me first thank Valerio Wait for this beautiful talk, and also for the long and constant effort he put in organizing this workshop, which wouldn't do without him. Thank you very much.
yeah.